Okay, here's a little quick explanation because some of you got a few bits and pieces wrong in the Google form question I gave you. So the first one is, what's the difference between long wave radio, radar, what's that going, radio, we'll have short wave, well we'll call that actually medium wave radio, that wasn't in the question but I'm going to do it anyway, and we had TV and radio, which are short wave, very short, or called very high frequency waves. TV and radio, and they're essentially very short waves radio. So long wave radio, here is the Earth, there is my antenna. If you remember, an antenna is basically just a wire with an electric current which goes up and down at a certain frequency. So it's just like an alternating current. It goes up, it goes down, it goes up, it goes down, it goes up, it goes down. And in doing so, it emits radio waves. Now these radio waves, if they are of a very low frequency, they have a very big wavelength. All waves travel at the same speed, v equals frequency times wavelength, if we remember that equation. If you've got a very small number there, and you must have a very big number there, but that number is going to stay the same. For example, I'll just put some numbers in there. Let's just say we've got a speed of 50. Well, I can either have 1 times 50, or I could have 50 times 1. Either way, the speed of electromagnetic waves all must stay the same. So if I have a low number here, I must have a high number there. If I have a high number here, I must have a low number there. So in other words, if I've got a low frequency wave, it must have a high or very big wavelength. So if this low frequency wave is emitted from the mast, if it's long enough, it can actually bend around the Earth in a process called diffraction. So it can diffract around the Earth, and it could then be picked up by this antenna here. And what it does is, as that wave passes through, it makes the electrons in that wire whiz up and down, up and down, up and down, and so you get a corresponding alternating current. This was all in that radio waves video that I did the other day. Medium waves are a bit different. All around the Earth is a layer of the atmosphere called the ionosphere. And in the ionosphere, if we take my radio antenna there, the ionosphere is able to reflect radio waves from one mast to another. So you can actually reflect these waves around the Earth. So that is by reflecting off the ionosphere there. TV and radio waves are very short wavelengths. So again, if we go back to that wave equation, if the wavelengths are short waves, that means they must have a high frequency, hence very high frequency waves to have the same wave speed. Just so you know, it's 3 times 10 to the power of 8 meters per second. That's the speed of all electromagnetic waves. Or writing that number out, it's 300 million meters every single second. That is halfway from Earth to the moon in 1 second. Anyway, back to TV and radio waves. They're too small to diffract, and they will not be reflected off the ionosphere. In other words, they will go all the way through the ionosphere. So there's not a lot you can do with these if you're around the other side of the Earth. they are just going to go straight out. So the only way that these can be used is if you are in line of sight of that radio wave. You can then pick that up in your antenna, which is the exact reason why we need to have TV masts situated on big hills in surrounding areas. So you'll have Fenton TV tower right in the middle of Fenton. You can see it outside my my classroom window, and if you can see it outside my classroom window, pretty sure all the houses around can receive it. So you get a very, very clear signal through TV and radio waves. Okay, last couple of things that need clearing up a little bit. And I'm just going back to your answers. Fluorescence, yes. If we go to fluorescence now, or fluorescent bulbs, this is about one of the uses of UV, or ultraviolet light. So this is in the electromagnetic spectrum. We've got radio waves, microwaves, then we've got visible light, then we've got ultraviolet, X-rays, and the very, very high frequency gamma rays there. Gamma, X-rays, UV. Visible light is a tiny little band there that our eyes can pick up. I'll call that just a V. We've got infrared, we've got microwaves, and we've got the radio waves we just talked about. If we look at UV, they've got some uses such as tanning. It causes your skin to age quite badly, but they're used in tanning. But they're also used for fluorescence. Oh, appalling spelling out. What is going wrong with me? Let me get rid of that. How embarrassing. Flu or fluorescent. Okay. Now, if we have a quick look at that, how these fluorescent bulbs work is, let's say we get a light bulb here. There's my light bulb. And inside is something in there that emits not visible light this time, but we're going to say, we'll call it violet. Let's find a purple colour. Yes, there we go, ultraviolet. It is going to emit ultraviolet light out to the edge of the bulb. Now, we can't see visible light, ultraviolet light, but what this bulb has is around the outside, it has a particular chemical coating that absorbs UV, and then it gives back out a longer wavelength of visible light. And that idea of something absorbing ultraviolet but giving back out visible light is called fluorescence. You can see it as well on security markers. So any forged banknotes, or real banknotes actually, have this chemical on, and you shine a UV light on. The UV light, I'll go back to my purple, high frequency goes into the chemical. The chemical fluoresces and gives out the longer wavelength visible light, and you can see it glowing. Final little one that I saw is a bit of a problem was mainly fibre optics, I think, a little bit. Although that was okay. Fibre optics was okay. So this is just for one or two people. Fibre optic cables are how your broadband receives the internet, and it's just an infrared type of electromagnetic wave, bounces off the inside of a plastic cable. We don't say bounces though, we say reflects. And it's actually a process called total internal reflection. In other words, all of it reflects inside.